Hi, my name is Kang Win, and I'm going to be talking about IV characterization and temperature dependence resistance behavior of NCO thin film. And this was all from the Nebraska Center for Materials and Nanoscience at the University of Lincoln, Nebraska. And it was under the supervision of Bhaskar and Professor Shaoshan. So to begin with, what is NCO? Well, NCO is a complex metal oxide made up of 1 part nickel, 2 part cobalt, and 4 part oxygen. NCO is grown in our lab using sophisticated technology called post-layer deposition method and are a high-quality thin film that can be used in supercapacitors, batteries, and sensors. And this piece in the middle right here, this square thin film, that would be the NCO. It's about 23 nanometers thick, which is super small. Its transport properties are voltage, current, and resistance. And these properties can be characterized using the Cathode 2400 source meter. Now, when it comes to measuring, there are many methods to do it, or just two, I guess. And first one would be the 2-wire method, where it only uses 2 wires in its name. So here, both terminals are used for supplying current and measuring the corresponding voltage drop across the resistor. And this, these two dots over here, these would be the terminals. So this arrow pointing up, that would be the ammeter, or what supplies the current. And as current is being supplied across the lead wires, resistance would be there since lead wires contain resistance. And then down towards the DUT, or the device under test, which would be the NCO. And then back towards the ammeter, where the voltmeter's job would be to measure the device under test and the resistance along the lead wires. Now, resistance from the DUT and terminals are added together at the end, showing how it has a higher resistance value compared to the 4-wire setup. This is the 4-wire setup. Well, the I value right here, again, this is the ammeter, and it runs current around the whole diagram on this outline only, as when it goes across the lead wires, it would have a bit of resistance, and then back down here towards the DUT, which would then go back around the ammeter. Well, the voltmeter, it measures the voltage drop across the lead wires. So it measures the resistance from the DUT only, because current runs across all three of these resistance value points, it can't go back up towards the voltmeter for these top and bottom wires, which means that the resistance from the bottom and the top lead wires wouldn't be added together, because the current that runs through the resistance doesn't go back up on the voltmeter because it has infinite resistance. So that goes along with this lead wire too. This is the reason why all four of these resistance values don't get added up. The current, even though it does or doesn't pass through it, it doesn't go back up towards the voltmeter because the voltmeter has infinite resistance. Although current does pass through the DUT over here, and once it does, the voltmeter does detect the resistance, because the current goes through this but doesn't go back up towards the voltmeter. Now, the VM terminals measures current on the DUT, as the voltmeter has infinite resistance, declining any current from reaching the voltmeter terminals, so there would be negligible potential drop across the lead wire connected across the potential measuring side. So this is the 4-wire setup, or the Cathode 2400. And this machine can measure both 4-wire and 2-wire. But for 4-wire, 4 terminals are connected to the source meter over here, where 2 is for the ammeter and 2 is for the voltmeter. The ammeter runs current down a 1 terminal, and through the sample, spreading it out the surface and back into the other ammeter terminal, where the voltmeter, however, measures the resistance of the DUT as infinite resistance, allowing the resistance between the voltmeter wires to be neglected as no current is passing through it. This is a graph of a 2-wire and a 4-wire measurement. So this is 2-wire, and for to start off with these equations right here, this value 20,377 is the resistance of the overall graph. And this value is can be taken by voltage divided by current, which is Y divided by X to get your slope. As this whole equation is basically just Y equals mx plus b. And AE minus O6, that's going to be your y-intercept, which shows you how to get this equation for this whole graph. And this type of measurement is mainly for higher and more accurate values of resistance, like cars, outlets, or supercapacitors. 2-wire measurement has a bigger value of resistance because it is measuring the wires itself along with how it is set up to transit current in a series of resistance. Now for 4-wire, it's the exact same thing, but the values of the linear equation is just a bit smaller. This type is mainly for smaller measurements because it can measure specifically a small resistance of sample without including the wire's resistance. It also contains smaller resistance because it neglects the wires that transit current to the sample, allowing it to measure the sample only. So, for example, if a DUT has a low resistance and the resistance of the lead wire is similar, then the value of the lead wire will not be neglected. This is why 2-wire for is only used for measurements for DUT, which are highly resistive, but for smaller resistance, even comparable with that of lead wires, we need to measure the resistance of DUT only. That is when 4 wires is significant. So to make this more clear, basically for 2 wires, um, or for 4-wire, if the resistor has, let's say, 10 ohms, but your lead wires is 5 ohms. So if you add all the lead wires together, that would equal 10. And 10 ohms of the lead wires plus 10 ohms of the resistor would change the resistance value dramatically, which isn't good for a 2-wire measurement because you want a more accurate value. But for 4-wire, it doesn't measure the lead wires resistance, which means that it can just be neglected. This is why 2-wire is better for bigger appliances because if a resistor has 1,000 ohms, but the lead wires are 5 ohms in total, then you can just ignore the small change in the resistance. So this is the RT measurement graph. So this graph visualizes what happens when temperature is increased or decreased on the material. So as you can see right here, this is resistance value, and it goes up to 7.00 E plus 3. And the bottom here is temperature, and this is in Kelvin value. So as temperature is going up, resistance value goes down because the covalent bonds are breaking and it's weakening as temperature is increasing. And once it starts to cool down, the resistance would start increasing because it goes back to its origin state, getting stronger with its covalent bonds. Now, the increments of resistance with decreasing temperature is exponential. And that's why the material is non-ohmic because of how the graphics exponential and when it can reacts to temperature change. So for a graph to be ohmic, it would have to be linear with a constant um resistance value because Ohm's law states that resistance has to be constant for it to be ohmic. Now, sensitivity of NCO. Well, sensitivity to begin with is the smallest amount of change needed to be easily detectable, while the response time in this matter is the amount of time needed for the origin to get to the saturation point. And for this graph, the initial resistance value is 714.51 ohm, which is down here. This is the origin or the start off value. And when it's in presence of acetone, it would go up to 716.72 ohms, which would get increased dramatically up here. And this is what we call the saturation point. Now, to find the sensitivity, you take your saturation point minus your origin, and you divide that by your origin, and you multiply it by 100%. That would give you your sensitivity, which in this case would be 0.3. And uh, to explain this graph further, this side is your resistance, and this is your time. So when acetone is introduced here, as time increases, the resistance value would also increase, but up until it gets to its saturation point and acetone is slowly decreasing, the value of the graph would also start to decrease down in resistance. Thank you for watching, and I appreciate your time.